So we're going to continue today talking about geologic time. And the first thing I'm going to talk about is the way that we interpret data. And so the way scientists interpret data, this is the only thing you're going to find in the textbook, is using what we call uniformitarianism. Uniformitarianism is the assumption that the Earth's geology is the result of slow processes over long periods of time, that natural laws have been constant throughout geologic history. How does that differ from what a young Earth creationist uses as their method of interpreting the data?
Can you repeat that?
How does this definition here of uniformitarianism compare to the method that a young Earth creationist uses to interpret the same data?
They assume that at some point in time the natural laws did not work the same way that some catastrophic events.
Okay, so she had two options which may be inclusive or exclusive. One is that at some point there's been a supernatural event that could be invoked, because if you are a creationist, creation is certainly a non-natural, i.e. a supernatural event, and that there may have been catastrophic events that have resulted in significant changes. One of the things that we like to say when we're talking about the two different ways of interpreting the data is uniformitarianism uses small amounts of water over long times, whereas the creationists generally use just the opposite. Large amounts of water over short times. A large amount of water in a short time will have a similar impact to a short amount of water in a long time. If you have a large amount of water, it causes much more erosion, and then when it stops, much more deposition. And so there are two different lenses, if you will, for interpreting the same data. So what do geologists find when they look at the long record? They find layers of rock with different kinds of fossils in them. That's what the data is. The rock may show signs of having like small pieces that are smooth and well sorted. You know, as you had in your homework, the smallest pieces would have been carried by air. Then you would have water carrying slightly larger. Water tends to be reasonably well sorted, whereas a glacier carries all different sizes and it grinds them so you have rough edges. So they can tell things about where the rock came from, if it's volcanic, tough. You know, they can look at those things and they find bones in them, and then they try to build a story. And when you're looking at all of the different layers of rock and the fossils in them, the best working, I suppose, creation story is that we had a worldwide flood, so we call it flood geology, and that this worldwide flood caused enormous erosion and very quick deposition. And so you have all of these layers of fossils that were all laid down in very close to the same amount of time, you know, like all within a year, right? Because the world was covered in water for roughly a year. And then they say, well, why do you have the different layers? Why do you only find at the very lowest layers this kind of animal, and at higher levels this kind of animal, looking at the fossils? And they say, well, it makes some sense that the small little fellers couldn't get away. And so, you know, the water's coming, run. They get washed away. But the bigger guys and ladies can run up the hills and get further separation, and so they weren't washed in until later. And so that's what they use to explain the separation of different kinds of fossils by the layers that were laid down. It's not a perfect theory, But then neither is uniformitarianism. You guys have probably heard, well, how many people have heard about the petrified forests that have vertical trees going through multiple layers of volcanic tuff? One. This here is used by creationists to say that those layers, the volcanic layers and layers in between, all had to be laid down reasonably close in time, or you should have the tree, completely eroded away. It doesn't go from here to here. That's like 100,000 years later, right? Because the tree doesn't live that long. And so they say that it must be evidence that it occurred quickly in a rapid deposition. And well, there have been lots of arguments back and forth, but that's one of the arguments that to me indicates, okay, there's a problem with the uniformitarian view because you just couldn't have the tree like that in the different layers. Okay, so that's enough of the background here. I just wanted to make sure that we have some understanding that what I'm presenting is the scientific view built on this uniformitarian model. And it's important that you understand where they get that from, but also it's important that you understand how people who believe in a young earth creation take the same data and come to a different conclusion. Now, the two dating methods, which we had a lot of questions on from last class period, relative dating versus radiometric dating. Relative dating is basically the original dating mechanism. You dig down, you find a new layer, and you say, in this layer, we have these kinds of fossils. And then you dig down lower and you say, in this layer, which has to be older because it had to dig down further, we have these kind of fossils. And geologists work very hard to try to identify layers. So you have a sequence of layers here, and you look somewhere else, and you have a sequence of layers, and they try to match them up, see if they're the same or if they're different. And if they're the same, then they say, okay, it's the same layer. We have it here and we have it here. So I might have it in Australia and I might have it in Mexico, the same layer. Now these layers, I'll get to you. These layers are not continuous. There's no place on Earth where you can dig and go through every one of the layers because you have to have the right conditions to form these sediment layers. You have to have, usually it's under a body of water. And so if you're not underwater, you're not going to be forming the layer. And you could have a layer that erodes. So you could have things like, here is a set of layers with 4 layers representing my fingers. And here is a set of layers. It only has 3. One of them's missing. Why? Because something must have happened in this region where you had erosion of this layer away. And so the next deposition was, missing a layer. Okay, what was your question, Brittany?
What are these what if all the layers are the same? How is that even?
Well, it would be one layer if it's all the same. And so when I talk about layers, I'm talking about soil that's the same type of soil. And so they go through and you have this kind of soil, and then you see a distinct break, and there's a different type of soil. And so that's what the layers are. And so you would just have one layer if there's no differentiation between it. Is that answer your question? Okay. So relative dating is just saying this one's older, this one's younger, based on the assumption of original horizontality, that the layers were all laid down horizontally with newer ones, of course, on top of the old. Radiometric dating is using what we've learned about before, using the decay rates of isotopes to calculate a time. And so you can take the relative dating and then assign actual numbers for the age using radiometric dating. So yes, here's that word, original horizontality. This is an assumption that everybody agrees, both creationists and evolutionists will believe that the sedimentary layers were laid down horizontally. They weren't generally laid down on hillsides because it would just run down the hillside with newer ones on top. So the superposition is the newer ones are on top, the older ones are below. Cross-cutting is an interesting feature. You can have an intrusion that breaks a rock layer. And so if an intrusion breaks a rock layer, we call it a crosscut, where you'll have something else that's going through a number of layers. Now, the example I use with the trees aren't going to be able to intrude in and make a crosscut. But if it's rock, you could have a fissure develop and rock come and fill it, a different kind of rock. You could have a crack with molten material that flows through. And so that's what these crosscuts are. And those will also help you to identify age because, if the material, I have the first clicker, the only clicker question is identifying which one's older and which one's younger. And I can illustrate the idea of identifying which one's older and which one's younger by just drawing two lines. These are kind of thin, so I'll make this one thicker so you can see. Just by looking at these lines, you can determine which one I drew first and which one I drew second. Which one would I have to have drawn first based on these lines?
Green.
The green. Right, you saw me do it, but why do you know it had to be the green? Because it was under the red. And so that's another principle we can use to determine relative ages of crosscuts in the rock. So keep that in mind for the one and only clicker question. An inclusion is when you have older rock in younger rock. That makes really perfect sense. I could have a rock that's been kicking around on the earth for, 4.5 billion years. And it rolls into a region where there's sediment forming. The sediment forms a layer of rock, but included in that is this really old rock. Right? That to me makes perfect sense. Now the reverse isn't going to happen. I'm not going to have an old sediment layer that has a young rock randomly inside of it. So it's important to understand that we can have inclusions. We can have older rocks included in the younger rock. Lateral continuity is what I was saying about if I have layers, I can have layers in Australia and layers in Mexico, and they can be the same layer. They're separated, but they're continuous. They're the same layer. And so we can talk about, the only thing that comes into my mind is coquino limestone. And we can find it over here. We can find it over there. We look at all of the layers around it and identify that's the same layer, even though they're separated. Faunal succession is talking about animals. It's saying that, yes, my dad taught me to separate these flora and fauna. A fawn is a baby deer, and so fauna is talking about animals. So faunal succession is basically saying that you should have life forms that existed in earlier times in the lower levels, life forms existed later times at the higher levels, and about the other way around. So it says irreversible time sequence. So here's just some pictures to illustrate how we get the ideal behavior. Here's our ideal behavior. We have a lake, and over time, different kind of material washed into the lake, floated down to the bottom, formed a sediment, and so you can see what we call the bedding, the different layers of rock in this lake bottom. That's the way that we teach in class. That's how it happens. And for good approximation, it is. But it doesn't stay that way necessarily. You could have a period of mountain building. What would cause this kind of deformation? I take this piece of paper. What's going to make the paper crumple up like that? If I compress it, yeah. So if you have compression, and so what would cause that compression? Something like the subduction of the Pacific plate under the North American plate, causing North American plate to push against other material until it buckles, forming the Rocky Mountains. Okay, question.
Okay, so I don't know, there's a picture, but like there's multiple layers that look the same. So what happens when you have layers of
you have to take a range. You can't just look at one layer. You have to take a range and look at the sequencing. Because so you do have, this layer here and this layer here look exactly the same, but they're separated. And so you would look somewhere else and say, do I have that same sequence?
Right, but how is that helping aging?
Well, if you can match, if I have the same sequence there as I have here, then I say those must be the same age. Right, so they match up because of the sequence. They match up to the same age. Now this here, we have mountains. We have anticlines and synclines. Remember, the syn is down, so these are synclines. So the anticlines are the other one. So this is an anticline here. But then what's going to happen to this mountain over time? What happens to everything over time on the surface of the earth? It decays. We have weathering and erosion, and so it's going to eventually be flattening out. Now, this is just a funny anecdote, really. When I was teaching at PUC, a person came and gave a talk about creationism. And the person gave an argument that it turns out is reasonably common, saying that you have erosional rates that decrease the height of mountains by, I don't remember what it's, something like an inch a year. And at that rate, if the earth is as old as they say it is, then you shouldn't have any mountains left. And here we have, the Himalayas, Mount Everest that sticks up so high. How is that possible? I wasn't there at the talk, but my colleague was, the other physics professor. And afterward, he comes up and says, well, the other mountains are there because mountains are currently being built. We still have the Himalayas growing taller. And the guy looked at him, what? Mountains grow? You have to know some basic things or else your argument sounds silly. He didn't know that mountains grow because of things like that compression making things buckle. And so the whole idea of mountains growing was novel to him, and he didn't think it was possible for there to be mountains because they can't grow. Yeah. Do you have a question, Justin? No. Okay, I thought you did. Okay, so we have erosion that flattens out the top. And then it goes underwater again. It goes underwater again. We form some nice layers on top. But now you look at the contacts. The contact is where one layer meets another. And you have things like this region right here doesn't exist on either side. Why? Because it was eroded out on either side, but since that was in a syncline, it had some of it at that location. And so that leads us to more understanding about some of the complexities of trying to match these things up, because you have some unconformities where you don't have the sequence perfectly reproduced. You have a missing layer here because it was eroded away between when one layer was placed and then the next layer. So does everyone see how you can easily turn up with having missing layers? Thank you. I appreciate when I get a response. Now, our one and only clicker question. 3 dikes. The dikes are the intrusions here. They're labeled dike A, B, and C. So they're cut into a rock body. Which dike is the oldest and which is the youngest? All right, everybody's answered. Since that's the only question, it was really important that I wait for everyone to answer, right? All 18 people said the same thing. So I'm going to assume that's correct, and I'm going to ask Stacy to explain why.
Well, an example of getting with the lines, the oldest one is the one that was beneath all the others. So C is the one that's underneath B, which is underneath A, so A would be the youngest one. And then C.
Because A cut through B, A had to be younger than B. And because B cut through C, C had to be younger, or B had to be younger than C, hence you get the sequence. So very good. Can't write with this one. Radiometric dating. I talked about this. I flipped back and forward through the slides, remember? So I got to this slide once before. Carbon-14 dating is really not useful to secular scientists. Why? Because it has such a short half-life. You can't really measure things beyond about 50,000 years old. At the very outside, using some extreme methods, you might be able to get to 100,000 years. And according to conventional science, hardly anything is that young. And so it's not useful to them. Now, if you're a young Earth creationist, somebody who believes that the flood occurred somewhere within the last 100,000 years, that gives you a whole lot of wiggle room for things like Usher's chronology to have some errors, then carbon-14 dating is highly relevant. So there are different interpretations of the relevance depending on your point of view. For the scientific approach, potassium-argon dating is very useful because its half-life is 1.3 billion years. So if you're looking at things that have occurred within the last 4.5 billion years, that's about 3 half-lives or less. So that's a really useful one. You see the uranium-235 has a much shorter half-life. Uranium-238 has a longer half-life. Those are also useful. If you look at these half-lives, we believe the Earth to be about 4.5 billion years old. So the amount of uranium-238 left in the Earth should be about half of what we started with. But if you look at the uranium-235, it has a half-life of 704 million. We've gone through, approximately 6.5 half-lives of that. So there's far, far less uranium-235. So when you dig up a rock with uranium, you're going to have a lot of lead because you see they end up with lead. And you're going to have very little uranium-235 because any uranium-235 it started with will have decayed away pretty much. Uranium-235 is the stuff that's useful for bombs. And so that's why they have uranium enrichment. You guys have heard of enriched uranium? Have you? Enriched uranium means they took the naturally occurring uranium, which is something like 99.7% uranium-238, and they have, through creating a chemical, they've made it into kind of a fluid, and then they centrifuge it, spin it really fast, and the uranium-238 is on the outside, uranium-235 is on the inside. They scrape the inside, and that's stuff they can use for bombs or power plants. The uranium-238, you can do things with it, but it's not as useful. You can make plutonium out of it. Neptunium first, then plutonium. The geologic timescale. I'm going to have this figure on like 10 slides at least coming up. We're going to look at it over and over and over again just because I want us to be reminded of the geologic timescale. So we have eons, our longest periods of time, then eras. Let's go to this one. So eons are the longest, then eras, then periods, subperiods, and then epochs. I was going to look up to make sure I know how to pronounce that. I always want to pronounce it epic, like it was an epic time, but I don't think that's right. So the eons are the longest times, and there's only 2 eons here. We have the Precambrian and the Proterozoic, Phanerozoic, Proterozoic is this here. The Phanerozoic. The Precambrian time is the time before there was much life on Earth. There is some life. If you look at these Down here, the Hadean, it's like Hades. Candace, describe Hades as you understand the term. What's it like there? Besides, I was going to say besides happiness spoke over you. What did you say?
It's like a term for hell.
Okay, it's a term for hell. So what kind of conditions would you have?
Freezing, fiery.
Extreme.
Fiery. The Hadean is based on that understanding. That was a time when the earth was pretty much melted, very hot, had lots of impacts, not hospitable to much life. Then you have the Archean, which is just the very old. And in the Archean, you have single cell fossils. And I'm actually going to show you, actually, I'm not sure if it's Archean or Proterozoic. Proterozoic, you start to have multiple cell organisms. And at the end of the Proterozoic there, you have a lot of little sea critters, things that we like to think look like cockroaches or pill bugs. And we call these things trilobites. And then right here, we have what we call the Cambrian explosion. Because at that time, when you look at rocks and you get to that level, you go from just having these trilobites, and if you ever go to Banff, you should totally take one of you can't hike there on your own. You have to have somebody leading you. Take a trip up to the Burgess Shale so you can see where they discovered these trilobites, which it's really awesome. And I have to tell you a useless story. The Canadians take law enforcement differently than we do in the U.S. So the day that we went up to see the Burgess Shale, they found some looters, people from another country, who had come and stolen some of the rock from the Burgess Shale. You're not allowed to take anything out. And so they had a big chase. Police are chasing everywhere. Royal Canadian Mounted Police are chasing everywhere, and they finally catch them. And just after they catch them, they get a call about something else. And so they tell those guys, now you stay here, we'll be back for you, and they take off and just leave them. What do you think they did? They took off again, and so then they had to have another chase to catch them again. Here in America, they wouldn't just say, now you stay, and expect you to stay. But it's a World Heritage Site, and so it's protected by international law, not just Canadian law. But it's very cool. Because you see these really old little pill bug looking things, and you can dig around a little. Yes, Raquel.
How much of this chart?
Oh, that's a very good question. For a class of this level, remember, like it told us not to worry about memorizing the periodic table. You don't need to worry about memorizing this. You need to know general themes, but you don't need to say, yes. 542 million years ago was when we had the Cambrian explosion, right? You don't need to know that kind of detail. You don't need to know, that's Silurian and, or Orvidician or whatever. You just have to know the general progression. We go from this kind of fossil to this kind of fossil. Helps? Good. Okay. Now in this table, you can see the Cambrian, we have the first fossil plants. First fossil plants, but it was dominated by fish. In fact, you know what? This entire Paleozoic was dominated by fish. Fish. So when we look through here, we're going to see some variations and some new things coming on. And so, we have the first plant fossils in the Cambrian. We have lots and lots and lots of fish fossils. Now, if we go through the creation story, because I want to make sure that we don't think that I'm just forcing the science down your throat, if we look at the creation story, what is the order of things being created in the Bible? Okay. First, God created light, said that it was good. Second day,
Was it like
he separated the waters above from the waters below. So he created the firmament, is what we learned as kids. You know, I didn't know what firmament meant. I just knew day 2 was the firmament. Day 3. Day 3 is dry land from sea and fish and grasses and stuff. So the stuff that we have there in the Cambrian is pretty much the day 3 things. And they continue on through that entire Paleozoic. So you go through, Cambrian, I actually went through and made my little mental picture to memorize this at one point. The Cambrian, Ordovician, Silurian, I can't speak English, Devonian, which to me has to do with the band. Anybody know the band Devo?
yes.
Do you know where they got their name from? It's actually pertinent here. Devo is a shortened abbreviation for de-evolution. They said that their band was a de-evolution of humanity, which might be why they wear the fun hats and whatever. The Carboniferous is often broken down into Pennsylvanian and Mississippian. Depends on who you are and where you are. And then the Permian, where you have the first reptiles. What was dominating the life? That is, what do we see in the fossils from the Permian primarily? Dominated by
Repeat yourself.
what's dominating the fossils in the Permian? No, that's the first reptiles, not what dominates. Fish. Right, all of these things in the Paleozoic are dominated by fish. Sorry, what?
I know it's something different, but
We thought it was different, but it was just.
Okay, so we have dominated by fish, but we have other things. The Pennsylvanian and Mississippian, there's a lot of coal in those. That's why it's called Carboniferous, because you get the coal from it. Pennsylvanian and Mississippian is because you have the kinds of coal you find in Pennsylvania, kinds of coal you find in Mississippi are where they get those names for those different subregions of the Carboniferous. Then we get to the Mesozoic, the middle, which we talked about is the age of dinosaurs. And we have the Triassic, the Jurassic, and the Cretaceous. The Cretaceous, I think that would probably be, Jurassic Park would probably be better called the Cretaceous Park. And then we have another switch. So this is reptiles, dinosaurs being an example of reptiles, dominate. And then up here we have mammals dominate. So when you're looking at the fossils, those are the kinds of things you find as you go up in layers. Now I'm going to go through probably pretty quickly because I spent a lot of time here on this one graphic to talk about it. Something very significant had to happen here. And something very significant had to happen here to change what's dominating. And what happened there, well, there's matters of conjecture, but I've got some pretty pictures, at least for one of them. I think it's funny. So we'll get there. All right, so now looking back at the Precambrian, the time before the Cambrian explosion, it represents 90% of the Earth's history. Remember the circle graph for the timeline we had last class period? 90%. So this little piece here is 90% of the Earth's history. Obviously, the times are not linear. Excellent. There we go. The times here are not linear, or else this would be almost the entire chart and everything else would be microscopic. There was a lot of volcanic activity there in the Precambrian. Of course, I said the Hadean, I mean, it was dominated by fire and brimstone, and it still continued on a lot of bombardment. Cyanobacteria and soft-bodied organisms are the things that are found in fossils. Cyanobacteria, they're bacteria that can survive in really crazy, harsh environments. If you go to Yellowstone and you look in those not geysers, but the hot pools they have, you find really pretty colors, right? Right?
Mm-hmm.
Those really pretty colors are caused by different cyanobacteria, different bacteria that can live in those ultra hot temperatures. And they're very sensitive to temperature, so different ones live in different temperatures, and that's what's giving them the really bright colors, which is very cool. And it's very shocking because we humans used to think nothing could live in those kind of temperatures. But now we know they can, just not us. Cyanobacteria, I think I assigned a homework question on cyanobacteria. They're an important part of the process of developing the earth to where it is now. The cyanobacteria, just like plants today, would take in carbon dioxide and metabolize it and spit out as their waste product oxygen. And so as a net effect, they were depleting carbon dioxide from the atmosphere and creating oxygen, changing the combination of gases that were in the atmosphere. And that's, of course, something that we have going on right now. Carbon dioxide levels are really going up, right? You've all seen the hockey stick graph. And with those carbon dioxide levels going up, what does that do to plants?
Makes them grow.
Yeah, it makes them grow much better. And so the plant's growing much better then produces a lot more potential food for humans and animals. And then we have, the creation of oxygen from that carbon dioxide, just like the cyanobacteria there. A word you probably haven't heard. In the Precambrian, we had a supercontinent, all the land masses together, in what has been named Rodinia, which is apparently Russian for the homeland. So you had a supercontinent. A lot of people knew the word Pangea, but it's not the only supercontinent. And so here's our first one, Rodinia. And you had the beginnings of lithospheric plate formation and movement. The beginning of making the plates that slide around to give us our plate tectonics. In the Precambrian time, here's some examples. This here is what we call stromatolites. Stromatolites are, it says right here, deposited by algae. And I had there the importance of cyanobacteria to make sure I didn't forget to say something. This here is an example of trilobites. So I don't see trilobite there, so I'm just going to write trilobite. And, they look kind of like cockroaches, right? Little sea creatures that scurry around the bottom of the ocean. Yeah, I kind of have that response as well. Important things about the atmosphere. The atmosphere we have now is roughly 21% oxygen and 79% nitrogen. But scientists don't believe that's always been the atmosphere. They believe that the primary atmosphere, the first atmosphere the Earth had, would just be from the common gases at the formation of the Earth. Well, the universe is like 90% hydrogen and virtually all the rest helium. So the primary atmosphere, they believe, would have been hydrogen and helium. But we've already learned that the Earth can't hold on to hydrogen and helium. So that primary atmosphere was lost because the Earth's gravity isn't strong enough to hold on to it. And so that was replaced by a secondary atmosphere that was gases baked out of rocks. So you have gases baked out of rocks, things like methane, as well as from comets hitting the Earth. Comets are icy rocks, and so that would give you the water part, whereas it would be the volcanic gases that give you the carbon dioxide part, probably. And so in the secondary atmosphere, We had water form liquid because it cooled down enough to form liquid water, dropping that out of the atmosphere. And then finally, we have our third atmosphere. The water removes the CO2 because the water will absorb the CO2 and then deposit it as rock. And so we end up with the tertiary or third atmosphere that is primarily nitrogen and oxygen. The development of O3 is important. Does anyone remember the name for O3? We have studied it. Ozone. And that ozone is important because it absorbs ultraviolet radiation as long as we don't put a catalyst with it. And so it makes it so we don't receive just blazing sunburns anytime we walk outside. So that's a good thing, having that ozone keeps us from getting sunburns all the time. And the sunburns, the radiation can cause mutations, blah, blah, blah. Okay, the Paleozoic has these. Like I said, you do not have to worry about memorizing them. It's just the sequence of going from one kind of thing dominating to another. So we'll just go through and look at these. Each one of those periods has different life forms that dominate, variations in the plate tectonics, differences in the air temperature and the sea levels. So the after the Cambrian explosion, you start having a bunch of fish. This doesn't say fish, I know, but you have hard-bodied organisms, things that are starting to make, calcium-based bones. And in the Ordovician period, which we have the dates for, you don't have to memorize those, we have the emergence of vertebrates, jawless fish. Fish that have a vertebra don't have a jaw. And so we start to see a lot of those showing up in the future. This is where they first show up. And you have a southern continent of Gondwanaland. So that's another supercontinent, Gondwanaland, situated very close to the South Pole. Why would you have widespread glaciation if you're close to the South Pole? That's where it's colder, right? Well, it wasn't just that. The whole Earth would have been colder then, we believe. But you have lots of glaciers during that time. It's a colder environment. Because of all the glaciers, you have ice forming, and so the sea level drops. And so you have the shallow water invertebrates lost their habitats. Bad for them. Here's a picture showing Gondwanaland down here. Now, it's not as big as it seems because with a map, the sizes vary depending where you are. And then you have Eurasia is the other part. So now this is looking into the Silurian period. And you have great things that you're all going to love, like scorpions and millipedes showing up. And, we can identify where North America was then. But notice North America and South America, they're not connected. North America is connected with Europe. And South America and Africa are connected, but not in the way that we tend to think of them as connected from where they are today. And notice China is very distant from Western Asia, which is distant from Siberia. Right? Very different geography. And of course, Australia is right there with China. So, going forward, we have the Devonian. Devonian is known as the age of fishes. You have the massive amounts of fishes that are found there. And the Eurasia is joined as North America and Eurasia joined for Laurasia. Okay, moving on. Then we get to the Carboniferous, and that's where Pangaea exists. If you look at the masses now, they're very different. Now you have North America and South America connected, with Africa filling in the gap. So the Gulf is where the hump of Africa is. Where I grew up, right there, would have been, very close to South America. And you see that Europe and Asia were connected to North America. Warm climate now. Dense swamplands. It's when it created all the stuff that's now our coal in the swamplands. Remember, we went through the coal cycle, and it started with the peat bog. And so that's what you had in Mississippi and Pennsylvania at that time. Great, plenty of insects. Moving forward. we have a big event to change it from being an age of fishes to an age of reptiles. Notice the numbers there. 95% of all marine species went extinct. We call this a mass extinction. About 70% of all land creatures went extinct as well. So you have almost all life on Earth ending. And it wasn't caused by humans. Now, this is, of course, based on the understanding of scientists, which is saying there's no God. So what would cause that? And we have possible causes here. You don't have to sit down and come up with them, but just think about this from the whole scientific method. Scientists notice that when they're looking at the rock, all of a sudden you get to this level, and almost every species you've been seeing disappears. And they're all, aha, I see something interesting. And then they want to explain, why did they disappear? And so, why did they disappear? The obvious answer is maybe they weren't living. There are other answers. Maybe they're now living in a situation that doesn't make sediment. If you have, like an animal that dies in a region that's not depositing sediment, it's not going to get buried and become a fossil. It's just going to decay and eventually be weathered, eroded away to nothing. So you have to be in the right situation to make a fossil. So you can't simply say, oh, they had to all die, but it does seem like a logical interpretation. And so possible reasons could be a redistribution of water and land, like some things went up above water, other things went down below, changes in the landmass elevations, climate change, or just lowering of sea levels. Now we're going to see in a minute, the end of the Mesozoic has another extinction that is, we think, much better understood. I say we think. That same time when I was up there in Banff, I went to a museum up there, and they had a display on the KT boundary. The KT boundary is the boundary between the Cretaceous and the Tertiary periods. And they suggested that maybe the best understood mechanism isn't correct. But we have three different periods in the Mesozoic, the Triassic, Jurassic, and Cretaceous, going from earliest to latest. It's the age of reptiles with lots of dinosaurs. So this has seas in Western North America. So, we have big oceans covering North America. It's underwater. And so we have ocean deposits in North America because it's underwater. Surprisingly enough, we have lots of whales up high in the Andes as well. Why would we have lots of whales high in the Andes?
The water covered most of the land. That was like that.
Okay. Now, do you suppose the water went as high as the Andes?
Yes.
There's not enough water to do that. The Andes had to be lower. This had to have been underwater at a time before the Andes were built. And so we have all of these whale fossils because that was a low level and the fossils were deposited, then it was raised up. So we have, during the Mesozoic, subduction of oceanic crust is causing the mountains to form in North America, and I think also the Andes. And so what do we have that's still alive from that period? Hooray, we have insects. Aren't you proud? We have reptiles, but you know what we don't have? Dinosaurs. Those kind of reptiles all died out. Flowering plants, true pines, and redwoods. The dinosaurs dominated and then they died. What made the dinosaurs disappear? Now, let me ask you a question. According to your understanding of the Noachian flood, where were dinosaurs during the flood? Not in the boat, she says. That's what I was raised believing as well. It turns out, the Bible doesn't tell us that. It comes from Ellen White. And if you go to the Creation Museum in, it's in, I think it's like Petersburg, Kentucky. It's right next to Cincinnati, Ohio. Ken Ham, who runs that, believes that dinosaurs were in the ark. And when I saw that, I was like, what? I thought every creationist believed that the dinosaurs died during the flood. But he believes the dinosaurs were one of the the dinosaurs were preserved on the flood, on the ark, and died later. Well, here is how we believe these dinosaurs. So I put this here so we have pretty pictures of dinosaurs, all the different variations. How they died. One day they're sitting there munching, having fights, killing each other, as long as they were not herbivores. When they look up in the sky and they see a big stinking rock, and that big rock hits the earth. In 1978, geologists found some structure down in Chicxulub, Mexico. They didn't know what it was. They actually gave up. But in 1990, it was identified as being part of the ring of a crater. And so further study shows this is not even in English. It's in, I believe that's Spanish. Like I speak any language besides English. It's not Spanish? Nope. Okay. French then? Anyway, you have this ring here, which is like the ring of the crater. Stuff that blew out of here extends out to that other line that's called the ring of ejecta. And you look at that and you say, how could that have caused all the dinosaurs to die? The answer is you threw up all kinds of crazy gases into the atmosphere. Those gases then are going to block sunlight, causing a change in temperature. They're going to change the quality of the air. And so, like if you have asthma, and you can't let the smoke get you because you got the asthma, it's going to kill you. And so it's believed that that's what caused the mass extinction. There's dating to go with it, but obviously I'm past time. So you can walk out, but I will answer the two questions. What do you want to ask?
Was it the meteor threw up gas?
The meteor would have been giving off some gases that was coming through the atmosphere, but that would probably be minor compared to when it hits the surface of the earth and you have huge amounts of soil flying up into the sky, as well as material that the meteorite was made with. One of the things that they use to identify this layer is in the KT boundary, they find, it's something like shocked silica. Quartz had a shock wave go through it. And there are some impurities, some atoms that we don't find naturally on Earth. They had to come from a meteorite. And so they say this layer was all laid down because of that material that was thrown up into the atmosphere that then settled everywhere on Earth. What was your question?
Why did it only affect dinosaurs, or did it?
Well, remember, with the mass extinction we saw before, 95%, this is not the same one, but 95% of ocean species and 70% of land, it's believed that the dinosaurs just were not robust enough to survive the changing conditions, while other animals, mammals specifically, were robust enough to survive the changing conditions.
Interesting.